Find the indicated term for the given arithmetic sequence. The 70th term of 6, 12, 18. So what we want to do is find the nth term of this arithmetic sequence. We have a formula for the nth term, and that's a sub n equals a sub 1, which is the first term, plus n minus 1 times d, and d is the common difference. So we have the first term of the sequence is 6. We need to find the common difference. So we'll look at consecutive terms and find their difference. And the first two terms are 6 and 12. When we take their difference, we get 6. When we look at the next two terms, 12 and 18, and we take their difference, 18 minus 12, we get 6. So the common difference for this arithmetic sequence is 6. So now we know that D is 6. So the nth term of this arithmetic sequence is 6 plus n minus 1 times 6. And with a little simplification, we get 6n minus 6, and combine like terms to get 6n. And now that we have the nth term of the sequence, we can find the 70th term of the sequence by substituting 70 into this. 6 times 70 is 420. So the 70th term of this arithmetic sequence is 420. Find the 5th term and the nth term of the geometric sequence whose initial term, a sub 1, and common ratio are given. We have a formula for the nth term of a geometric sequence, and that's a sub n equals a sub 1 times r to the n minus 1, where r is the common ratio and a sub 1 is the first term. We're given both of those things, so our nth term of this sequence is negative 9 times 5 to the n minus 1 power. And then if we want to find the 5th term of the sequence, a sub 5 is negative 9 times 5 to the 5 minus 1. That's negative 9 to the 5 times 5 to the 4th power. 5 to the 4th power is 625, and times negative 9 is negative 5,625. The 5th term in the sequence is 5,625. Write a formula for the nth term of the following geometric sequence: 4, 16, 64, and 256. The nth term of a geometric sequence can be found by doing a sub 1 times r to the n minus 1, where a sub 1 is the first term and r is the common ratio. The first term, a sub 1, is 4. We just need to figure out the common ratio. So if we look at consecutive terms and find the ratio, for the first two terms, 16 over 4 would be 4. Looking at the next pair of terms, 64 divided by 16 is also 4. If we look at the next pair of terms, 256 over 64 is also 4. So we get that the common ratio, r, is 4. So we can write the formula for the nth term to be 4 times 4 to the n minus 1. And then we can, since those have the same base, we can actually add those together. And that's 4 to the 1 plus n minus 1, and that's 4 to the n. So the nth term is 4 to the n. Use the principle of mathematical induction to show the following statement is true for all natural numbers n. With the principle of mathematical induction, there are two conditions that we need to prove. Condition 1 states that the statement must be true for n equals 1. And condition 2 is an if-then statement. It says if the statement is true for some k, then the statement is true for k plus 1. So we need to prove both conditions in order to say that this statement is true for all natural numbers. So let's start with condition 1. We need to prove that this statement is true for n equals 1. This statement is 14 plus 28 plus 42 plus ... plus 14n is equal to 7n times n plus 1. So for it to be true for n equals 1 on the left we're adding up the first n terms of the sequence 14n. And so since n equals 1, we're only adding the first term of 14. So the left-hand side is 14. We want to see if that equals the other side of the equation, where we have 7 times 1 times 1 plus 1. That's 7 times 2, which is 14. So since 14 equals 14, we've just proven that this statement is true for n equals 1. Then we need to prove condition 2. Since condition 2 is an if-then statement, we have a portion of the statement that we're going to assume to be true, and that's this part, if it is true for some value of k. So we're going to assume true for some value k. So that means that 14 plus 28 plus 42 plus ... plus 14k equals 7k times k plus 1. So we're assuming it's true for some value of k. We need to prove that this statement is true for k plus 1. Now what that looks like is 14 plus 28 plus 42 plus ... plus 14k. We need to go one more term, 14 times k plus 1. And this is going to equal 7 times k plus 1 times k plus 1 plus 1. So the statement that I'm trying to prove goes one more term in the sequence on the left, and on the right, instead of k, I use k plus 1 here, and instead of k here, I use k plus 1. So that's the statement that I'm trying to prove. So to prove that statement, I'm going to start from one side of that statement, one side of that equation, and I'm going to manipulate it to try to get to the other side. So I'm going to start with 14 plus 28 plus 42 plus dot 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 plus 14k plus 14 times k plus 1. Now what I can do is use substitution. Because I've assumed that this statement is true for some value of k, that means I have this piece of information right here. I can take all of this and change it to the other side of the equation because we assumed that it's true. So that would give me 7k times k plus 1 plus 14 times k plus 1. I'll use the distributive property to get 7k squared plus 7k plus 14k plus 14. I can combine like terms to get 7k squared plus 21k plus 14. I can see that all these terms have a common factor of 7. Factor that out to get k squared plus 3k plus 2. And that can be factored more. K squared plus 3k plus 2 factors into a binomial times a binomial. And that's k and k, 1 and 2, with both pluses. And hopefully you can see that I've now got to the other side of the statement that I wanted to prove. So now that I've met condition 1 and condition 2, I've proven condition 1 and condition 2, I can now say that the statement is true for all values of n, all natural numbers n. Evaluate the expression 5 choose 2. The symbols here are a way of expressing what we call a combination formula. And the combination formula goes like this. We have n objects, and we're going to choose j of them at a time. The number of ways they can be arranged is n factorial divided by j factorial times n minus j factorial. So for our example, we have n as 5 and j as 2. So that's 5 factorial over 2 factorial times 5 minus 2 factorial. We can simplify that to be 5 factorial over 2 factorial times 3 factorial. That's 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 3 factorial is 3 times 2 times 1. We can do a little canceling here. 3's cancel, 2's cancel, 1 cancels, and 2 goes into 4 2 times. And all I'm left with is 5 times 2, which is 10. So 5 choose 2 is 10. This TI calculator has the combination formula built into it. We can go, first you want to type the 5, which is the value of n. Then you go to the math menu and over to probability. And option number 3 has NCR. That's your combination formula, so I'm selecting number 3. So I typed 5 first because the 5 is next to the N, and now I need to type the J, or using this formula is the R, and it'll compute the combination formula with those two values. Expand the expression using binomial theorem. X plus 2 to the 6th power. So first let me write down what binomial theorem says. Binomial theorem says if you have x plus a to the nth power, that can be written as the sum of j equals 0 to n of n choose j times x to the n minus j times a to the j. So I want to write this in the context of our problem. We have x plus 2 to the 6th power. So we're going to sum from j equals 0 to 6. N is 6, so we're doing 6 choose j, x to the 6 minus j, and a to the j. So we're going to start by substituting a 0 into this sequence, and we're going to keep climbing up 0, 1, 2, and so on until we get to 6. So substituting a 0 in, we would get 6 choose 0, x to the 6 minus 0, and a to the 0. And I apologize, this a right here for our example is a 2. This 2 right here. So let me fix that. This should be a 2. Then I'm going to do the same thing except with j equal 1. 6 choose 1, x to the 6 minus 1 times 2 to the 1. Then we'll do it with j equals 2. 6 choose 2, x to the 6 minus 2 and 2 to the 2. Plus 6 choose 3 times x to the 6 minus 3 times 2 to the 3. Then we'll do j equals 4. 6 choose 4, x to the 6 minus 4 times 2 to the 4. Then we'll let j equals 5. 6 choose 5, x to the 6 minus 5 times 2 to the 5th. And we have 6 choose 6 times x to the 6 minus 6 times 2 to the 6. Now we've written out the entire sum from j equals 0 to 6, and we need to simplify all the parts. So we can calculate 6 choose 0, I'll do that up here. 6 choose 0 with the combination formula is 6 factorial over 0 factorial times 6 minus 0 factorial. That's 6 factorial over 0 factorial, and 0 factorial is 1, and 6 minus 0 is 6, so we have a 6 factorial in the bottom and on the top. So this is going to cancel out completely to be 1. So 6 choose 0 is 1. Then we have times x to the 6th power times 2 to the 0 power. 2 to the 0 power is 1. Then we need to calculate 6 choose 1. With the combination formula, that's 6 factorial over 1 factorial times 6 minus 1 factorial. That's 6 factorial. 1 factorial is 1. 6 factorial, 6 minus 1 factorial, that would be 5 factorial. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. So we have a bunch of factors that cancel out. So this combination formula simplifies to be just 6. So we have 6 times x to the 5th power times 2. Then we want to calculate 6 choose 2. Let me do that here. 6 choose 2 would be 6 factorial over 2 factorial times 6 minus 2 factorial. This is 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 6 minus 2 is 4, and 4 factorial is 4 times 3 times 2 times 1. So once again, we have a bunch of stuff canceling out. And then 2 goes into 4. Oh, sorry, 2 goes into 6 3 times. And that simplifies to be 15. So we have a 15 x to the 4th times 4. Now we want to find 6 choose 3. That's 6 factorial over 3 factorial times 6 minus 3 factorial. That's 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 6 minus 3 is 3, so we have another 3 factorial. We have a bunch of stuff canceling. 3 times 2 is 6, that cancels with that 6, and we're left with 20. So we have 20 times x to the 3rd times 8. So let's do 6 choose 4. That's 6 factorial divided by 4 factorial times 6 minus 4 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 6 minus 4 is 2 factorial, and that's 2 times 1. So 4, 3, 2, 1 cancels from the top and bottom, and 2 goes into 6 3 times. So 3 times 5 is 15. So we have 15 x squared times 2 to the 4th, that's 16. So let's calculate 6 choose 5. That's 6 factorial over 5 factorial times 6 minus 5 factorial. 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. 6 minus 5 is 1, and 1 factorial is 1. So 5, 4, 3, 2, 1 cancels, leaving me with 6. And we have 6 times x times 32. 2 to the 5th is 32. Then we want to calculate 6 choose 6. So 6 choose 6 is 6 factorial over 6 factorial times 6 minus 6 factorial. And 6 minus 6 is 0 factorial. 0 factorial is 1. And we have 6 factorial over 6 factorial, so those will cancel, leaving me with 1. So we have 1 times x to the 0 times 64. So almost there, just a little bit more simplifying to do. So we have 1 times x to the 6 times 1, that's x to the 6. 6 times 2 is 12 times x to the 5th. 15 times 4 is 60, x to the 4th. 20 times 8 is 160, x to the 3rd. We have 15 times 16, and that's 240, x squared. 32 times 6 is 192x. And 64 times x to the 0, x to the 0 is 1, so we just have 64. And that's our expanded binomial, x plus 2 to the 6th power. I'm sure you could see that as we did this, the part that took the longest was working out all of these combination formulas. I do have a little shorter way for you to work out what these values are, and it's something called Pascal's triangle. In Pascal's triangle, you start with a 1 at the top of the triangle, and in the next row, you're going to have 1s, 2 1s. On the third row, you're going to have 1s on the edge, and then a number that you put in the middle of those two. And you get that number in the middle by adding the two numbers from the row above. So 1 plus 1 is 2. Then in the next row of Pascal's triangle, you put 1s on the edges again. And this time you're going to have two numbers to fill in here. And once again, you're going to get that by using the two numbers from the row above. So 1 plus 2 is a 3. 2 plus 1 is a 3. We're going to continue building this Pascal's triangle. We have 1s on the edges, and now we're going to have 3 numbers in the middle. We get these numbers from the row above. That's a 4. From the row above, 3 and 3 add up to be 6. From the row above, 3 and 1 is a 4. Let's do another row of Pascal's triangle. That's 1s on the edge. This time we're going to have 4 numbers. We're going to use the 1 and the 4 to create 5, the 4 and the 6 to create 10, the 6 and the 4 to create 10, and the 4 and the 1 to create 5. Now one more row to go, 1 on the edge, and we're going to have now 5 numbers in between. And this number comes from 1 and 5, that makes 6. 5 and 10 is 15. 10 and 10 make 20. 5 and 10 make 15. And 5 and 1 make 6. Now hopefully you noticed that this last row of Pascal's triangle that we worked out contained the coefficients that we got from using the combination formula. 1, 6, 15, 20, 15, 6, and 1. So if you're able to build Pascal's triangle, you can use those numbers in your binomial expansion without having to use the combination formula. The way you decide which row you're going to use is based on the power of your binomial. So for this example, we're raising to the 6th power, and you're using this row right here for n equals 6. the first row starts with n equals 0.